Okay, so we will begin our lectures on time-dependent perturbation theory. So we are already used to the time-independent perturbation theory. So let us quickly recap the philosophy behind time-independent perturbation theory. So time-independent perturbation theory. You start with a Hamiltonian H, which is an exactly solvable part plus a small part that is a little difficult for you to solve exactly, right? So suppose if I am able to solve h0 plus h prime exactly and get the eigenstates and eigenvalues, then of course I don't need any perturbation theory, right? So the whole point of perturbation theory is that this Hamiltonian, to get the eigenstates and eigenvectors, eigenvalues and eigenvectors of this Hamiltonian is a little difficult. Okay, so this is why we resort to certain approximation techniques, and one approximation technique is time independent perturbation theory, where we claim that the part that you add to the solvable Hamiltonian H0 is small in strength compared to H0. The way we usually adjust this is with putting in a small parameter lambda and adjust the value of lambda something between 0 and 1, right? So if lambda is a small parameter, then I can understand the eigenstates of the full theory as sort of an expansion. So the first order state should be the eigenstate of the unperturbed Hamiltonian H0, and then lambda times the first order correction plus lambda square times second order correction, and so on and so forth, right? And similarly for the eigenvalues. So you substitute this in the eigenvalue equation and develop a perturbation series in powers of lambda, right? And then you solve order by order in lambda in a self-consistent fashion, and you calculate the first order correction to energy, second order correction to energy, first order correction to the wave function, and so on and so forth. So this is what you do typically in time independent perturbation theory. And the whole point behind this is that the H that you write down is not solvable analytically. So that is the reason why you resort to such approximation techniques. So the time dependent perturbation theory is a similar problem, but slightly trickier. So today we will try to attack the time dependent perturbation theory in a fashion that is similar to time independent perturbation theory, but we will quickly move on to a different way of setting up the problem and getting the solution for this particular case. There is a more powerful technique to understand how to solve time dependent Hamiltonians, and one uses what is called the interaction picture. Okay, so far you have been used to the Schrodinger picture, the Heisenberg picture, but I will introduce a third picture that is actually very helpful for us to understand time-dependent Hamiltonians. But this is later. Today we will actually stick to the basics and simply talk about time-dependent perturbation theory in a fashion that is analogous to the time-independent stuff. Okay. So how do I set up the problem? So set up. So the proviso is that I am now given a Hamiltonian H, which is the unperturbed Hamiltonian, just like I had initially, but a small perturbation, H tilde. The only complication here is that this could be a time-dependent perturbation. For example, you could take a hydrogen atom and subject the hydrogen atom to some electromagnetic pulse, right? So some time-dependent electromagnetic wave, right? E to the I omega t kind of stuff. So how does the hydrogen atom behave under these external perturbations? That is the question that we have to answer. Now, remember that this throws a monkey wrench into the whole business, because the way we solved the Schrodinger equation, remember when we wrote down the Schrodinger equation, right, for the time independent part, how did we write it down? We said IH bar d dt of psi is h0 psi, right? And then we introduced the separable method, and we wrote the solutions as something that depends only on position and something that depends only on time, right? And the reason is because H0 itself was time independent. So this is the reason why the time part was actually easier for us to solve. And we got what are called stationary states. What are stationary states? The stationary states, for example, have definite energy. Definite energy. So let's call them N0. The 0 indicates that these are the eigenstates of the unperturbed Hamiltonian. These have definite energy, which I will call En0, right? And the way they evolve in time is after a certain time, the state evolves to a new state, which is given by e to the what is it, minus I En0 t over h bar n0, right? So this is the basis behind solving the time dependent Schrodinger equation. You piece it up into a time dependent part and a space dependent part, and then you then go on and solve the time independent Schrodinger equation to get the positional dependence, and then you just tag on the time dependence and claim that the stationary states evolve according to e to the minus in0 t over h bar times n. Okay. So notice that in this picture, if you start with a state n, the state n after some time doesn't evolve to a state m. Okay. In other words, after a certain time, n0 does not time evolve into a different stationary state, let us say m0, right? N0 remains N0 with the time dependent Hamiltonian, with the time dependent part, which is just oscillatory, e to the minus IEN0 t over h bar, right? The reason is because, of course, these are all orthogonal states, so the overlap of N0 and M0 is just 0, right? So this is all something that you already know, but this is all going to change if I introduce an explicit time dependence into the Hamiltonian. Okay, so this whole idea of breaking it up into this and that, and then claiming that stationary states are just e to the minus in0 t over h bar, it's not going to work because we have to solve the differential equation itself differently, right? So in other words, if I have a time dependent piece in the Hamiltonian, if h tilde of t is non-zero, then n0 are no longer the stationary states. This is fairly obvious of the system, right? So now there is two things one can do. The most straightforward thing one can do is just if we need to solve the Schrodinger equation I h bar d dt of psi of t equals h psi, and this is equal to h0 plus h tilde of t psi. And if you're really good at differential equations, you can just take this and solve it straight away. But the point is, for most time-dependent Hamiltonians, this differential equation is not really straightforward to solve. So this is why we need an approximation technique, just as we discussed for the time-independent case. Even though it looks fairly innocuous in a general setting, such time-dependent problems are really hard to solve as solutions of differential equations. But that's not to worry, because in most practical cases, it also turns out that the time-dependent Hamiltonian, the strength of the time-dependent Hamiltonian H tilde, turns out to be weak compared to the time-independent stuff. So just like we developed a perturbation theory for time-independent Hamiltonians, we can also develop a perturbation theory for such time-dependent Hamiltonians. The question is, how do you develop this perturbation series, and how do you calculate the corrections to the energy eigenvalues and the wave functions? Okay, so this is the problem. Is this clear?
Sir, can you please just explain once again that why doesn't N0 evolve into some other stationary state?
Okay, so remember your Schrodinger equation. Okay, So how do you solve the Schrodinger equation? So you start by saying IH bar ddt of psi is H0 psi, right? I'm calling H0 because I'm manifestly looking at time independent Hamiltonians, right? Now, you can actually go into the position representation and write this as IH bar d psi of x comma t dt equals minus h bar square over 2m del square plus v of x psi of x comma t, right? And then you claim that psi of x comma t is some f of t and g of x. Agree? And then you substitute this back into this equation, and then you develop, instead of a partial differential equation for psi, you have total differential equations for f and g. Agree? So in particular, we have something like e d square f over dt square is some minus something times f, which gives you a exponential, an oscillatory dependence on time. So f of t, you say, is just e to the minus I e t over h bar. Agree? And then for the spatial part, you actually solve the time independent Schrodinger equation, h psi of x t equals E0 psi of x comma t, right? And then you say that the solutions of these, for example, could be some n zeros, each having a definite energy En0. So far, so good?
Yes, sir.
Yes or okay. Now, so which means that the solutions of the time dependent Schrodinger equation can be written as a series of stationary states. So psi of x comma t in general can be written as Cn e to the minus I En0 t over h bar psi n of x. Agreed? Where this is a solution to the time independent Schrodinger equation, and this is the time dependence. Okay. Now, psi of xt itself is a linear superposition of all these stationary states. But if you look at any one stationary state, so for example, if the system starts out and the state, let us say, with a particular, so let us say at time t equal to 0, the wave functions, initial state wave function of my state of my system is, let us say, so let us actually use a different symbol for the, oops, in case you're confused, let us call these stationary states phi's. Okay, psi of x comma 0 equals, let us say, phi 3 of x. Okay, so this is a 0 in case it is not. Okay, and now I ask, what is psi of x comma t? Okay, now there is no way that psi of x comma t would be something like, for example, e to the minus I e1 t over h bar phi 1 plus minus e3 t over h bar phi 3. This can never happen. Why? Because my state already starts out as one of the stationary states, and I exactly know how stationary states time evolve. I will simply tag on the time dependence of the stationary state. So psi of x comma t would not be a linear superposition of the time evolved phi 1 plus time evolved phi 3. If my state starts out at phi 3, there is no way I can get a phi 1 later. Does this make sense?
Yes, sir.
So, but suppose my state starts out, let us say psi of x comma 0 was, let us say, 1 over root 2 phi 3 plus 1 over root 2 phi 5. Okay. And now I ask, what is psi of x comma t? Psi of x comma t, since I already know that the state, initial state, can be written as a superposition of two of the stationary states, my psi of x comma t would be phi 3 e to the minus I e3 t over h bar plus phi 2 e to the minus I e2 t over h bar, right? This is the answer. In fact, you guys have solved many problems like this, right? But I cannot, for example, write plus something phi 8 e to the minus I e8 t over h bar. Such a term can never appear because the evolution of stationary states doesn't cause any mixing between stationary states. If I start out at this in a particular stationary state, I remain in that particular stationary state, right? Unless I disturb the system by making some kind of a measurement, there is no way, if left to itself under the action of a Hamiltonian, one stationary state can become another stationary state. That is not possible. This is what I mean by that statement. Is this clear?
Okay, yeah, sir, I got this. But can we not this phi 3 with this exponential? Can we not, just define it to be some other state?
No, because I've already told you exactly what the states are. See, I've solved, these are not some arbitrary numbers, right? I've actually solved h phi n equals e n phi n, and I've told you what the phi n's are. Phi 1 is a definite state with an energy E1, phi 2 is a state with a definite energy E2, and so on and so forth, right? See, I have given you some Hamiltonian H0 with some potential energy, I don't know what, but you have solved the time independent Schrodinger equation and told me what the energy eigenvalues and energy eigenstates are, right? Those are these phi n's. Now I can write down the general solution as a linear superposition of all these stationary states, right? This is what you usually do. That is a different issue. But the question that I'm asking is different. Suppose if my general state is not a linear superposition of all the stationary states, suppose if I prepare my system such that at time t equal to 0, my system starts out at any one particular stationary state, let us say phi 3. So it is not a general linear superposition. My initial state is such that the system itself starts out in one of these stationary states. Okay, let us say phi 3. And now if I ask how the system time evolves, psi of x comma t would be phi 3 e to the minus ie3 t over h bar. There is no way I can get a phi 1 component or a phi 8 component. Okay, see, remember the general kinds of problems you have solved in the first semester. You know how to solve the time independent Schrodinger equation. You know how to solve this, right? Now, suppose I usually give you that at time t equal to 0, psi of x comma 0 is some f of x, right? And now I ask, what is psi of x comma t? This is the typical problem that one asks, right? In fact, you guys, if you can go back and look at your notes, you would have solved a lot of problems like this. How do you attack these problems in general? Well, you say that, look, the phi n's are the solutions of a Hermitian operator, the eigenfunctions of a Hermitian operator. So they form a complete set, orthonormal set. So I can expand any function as a linear combination of phi n's, right? So you say, well, I'm not going to use the function that you gave me. Instead, I'm going to write this function as a linear combination of the stationary states of the whatever Hamiltonian I have at hand. Okay. And now how do you calculate these CNs? Well, you know that the CNs can be written as phi n star f of x dx. So you know how to calculate the CNs, right? So now, instead of starting with the function that I give you, you're going to re-express that function as a linear combination of the stationary states of the system. So you're going to say psi of x comma 0, the function that you gave me, can be instead understood as, let us say, some 2 over root 3 times phi 3 plus, let us say, what is this? Square root of 2 over root 3 and square root of 1 over root 3 phi 5. Okay, so you have done this linear combination and you have found that all CNs except for C3 and C5 are 0. Okay. So once you have done this part, psi of x comma t is very easy for you because you simply say psi of x comma t is just phi 3 e to the minus e3 t over h bar plus 1 over 3 phi 5 e to the minus I e5 t over h bar. So what is the assumption here? The assumption here is that once you know that the state starts out as a linear combination of phi 3 and phi 5, the time evolved state can only have phi 3 and phi 5. It cannot have anything else. In other words, if phi 3 evolves to, let us say, a linear combination of phi 3 and phi 7, then you're screwed. Then that will be difficult to solve. But that doesn't happen because phi 3 and phi 5 are stationary states. and you know exactly what their time dependence is. They are just e to the minus iet over h bars. So to figure out the time dependence of this wave function is simply tag on the oscillatory functions e to the minus iet to every stationary state, right? This is how you typically solve the problem. But suppose if this turns out to be plus something times phi 7 e to the minus e70 over h bar, then this is a very different answer. This doesn't happen. There is no way. If you start out with a definite combination of stationary states, you would get a different stationary state down the line. Okay, that will not happen. So this is what I mean by saying that a stationary state will remain in that stationary state under time evolution. Of course, if you start with a state that is a linear combination of stationary states, that state will stay as the same linear combination of stationary states as time evolves. The only difference is you have to tag on the time dependence here. That is all. Make sense?
Yes, sir. Got it.
So in other words, if I psi of x comma 0 is phi 3, then psi of x comma t, there is no way this can be equal to phi e to the minus I e phi t over h bar. This doesn't happen. Okay, this is what I mean, simply speaking. Okay, so let me erase this part. Where did I go? Okay. Okay. So I need to solve the general problem. So how will I solve the general problem? So the way I will solve the general problem is like this. So I will claim that, look, I am in some Hilbert space, but I'm always free to choose the basis vectors of my Hilbert space, and my initial H0, which is not the complete Hamiltonian anymore, but the initial H0 still furnished me a set of basis vectors, right? So H0, N0 equals En0, N0. And these N0s are orthonormal basis vectors. In other words, M0, N0 is just delta NM, right? So I can still use these guys as basis vectors. Suppose if this H tilde T were not there, then I can write my psi of T as sum over N, sum e to the Cn e to the minus Ent over h bar N0, right? This is exactly what I just wrote down in a couple of minutes before. I can always write down the general state as some linear combination of the stationary state with the corresponding time dependence tagged along, if h tilde of t is equal to 0, right? So if h tilde t is not equal to 0, I can still write the general state as a linear combination of the n zeros, but my time dependence of the states is going to be different. They are not going to be stationary states anymore, so I cannot simply write down a simple e to the minus int over h bar. So if h tilde t is not equal to 0, then psi of t can still be written as some linear combination of the states. Let us say some alpha n of t, n0, but I need to figure out this alpha n of t. Okay. In other words, if at time t equal to 0, when there is no perturbation, I can still write psi as a linear combination of the stationary states. Now, at time at time t not equal to 0, the presence of the h tilde is going to make the time dependence a little more complicated. Okay. Now, I would like to understand what part of this alpha n of t arises because of the presence of h tilde t, and what part of this time dependence is because of the h0. Remember, if I did not have any h tilde, my time dependence will only go as e to the minus Ient over h bar. So I want to peel off the dependence of time because of h0 from the time dependence arising out of h tilde. The way I do this is I write the state psi as I write this time dependence as some dn of t e to the minus I en0 t over h bar n0. What have I written? Well, I've written some arbitrary function of time alpha n of t as another arbitrary function of time dn of t times e to the minus I en0 t over h bar. I strictly don't need to do this, but it is advantageous to do this because this way I know that this dn of t, whatever this time dependence is of the state, this arises solely due to the presence of h tilde of t. Okay, and this time dependence is usual time dependence due to h0. So this way I can keep track of what is what. In other words, all I am claiming is that if I figure out what dn of t is, I've solved the problem. Okay, ultimately my goal is to understand how the vectors evolve in time, and for this I know n0, right? N0 is something you already know because you have solved the time independent Schrodinger equation. En0 t over h bar is also something you already know because you know what the eigenvalues of these original states are. The only thing that you don't know is dn of t. So if we can figure out what dn of t is, we have solved the problem. Okay. But this is easier said than done. It is not very straightforward to solve the dn of t in a closed form. So to do this, we need to resort to perturbation theory. But how we resort to perturbation theory, I will explain as we go along. Is this part clear? Is the setting up of the problem clear to everybody? Is there any questions?
Sir, can we always write alpha n as dn times this exponential?
Yeah, absolutely. See, because this is some function of time. Okay. So let us say f of t turns out to be some at plus bt square. Okay. Sorry, let us say that alpha n of t is some at plus bt square. Now I wrote alpha n of t as dn of t times e to the minus en t over h bar, right? So if I solve for dn of t, I will get dn of t equals at plus bt square times e to the I en0 t over h bar. This is how I should typically get it. If I substitute this value of dn of t over here, you would actually see that the exponential cancels and you get at plus bt square. So it is just a multiplicative function, right? So I can always write one in terms of the other.
Yes, yes, sir.
Okay, so how do I figure out dn of t? So the way you would do this is by first recognizing that the Schrodinger equation for this system is d dt of psi equals h0 plus h tilde acting on psi, okay, which I can rewrite as d dt minus h0 minus h tilde acting on psi equals 0, right? So this combination turns out to be a null operator. It acts on a general vector to give me 0. So I will take this null operator and act it on equation number 1 on both sides. On the left hand side, of course, if this operator acts on psi of t, as we have just discussed, it gives me 0. Okay. So on the right hand side, this is ih bar d dt minus h tilde of t acting on dnt. So we should write all these three terms carefully because all of them are important. Okay. Is this clear? So my goal is to set up some kind of a differential equation for dn of t. That is why I'm doing all these tricks. Because I cannot simply look at this equation and figure out dn of t. So you might actually think that, well, what's the big deal? We can just take the overlap of psi with some m and use the orthogonality. See, if you take equation 1 and let us say you take m0 psi of t, right? And then you say that, oh, this is equal to n dn of t. This is what you usually do, right? En0 t over h bar. and this is m0 n0, and this is just delta mn, because you know these states are orthogonal. So this simply gives me, and then you will claim this is basically equal to dm of t e to the minus I em0 t over h bar. And then you will claim, oh wait, I've solved the problem. But you have not solved the problem, because I still don't know what psi of t is. You see, if you do it this way, psi of t itself is, I need to figure out dn of t to figure out psi of t, right? So any formula for dm of t that explicitly has a psi of t is not of much use to me, because I need to figure out psi of t in the first place. So this usual trick of just taking the overlap doesn't help us much. So we have to resort to some other trick. Okay, that some other trick is whatever that I'm doing right now. Okay, so let us carefully look at how these three operators act on this combination of functions and vectors on the right hand side. So n0 is a time independent, is a solution of a time independent Schrodinger equation. So ddt doesn't hit n0. But it does hit dn of t and e to the minus I en t over h bar. So I h bar ddt acting on dn times e to the minus en0 t over h bar times n0 would give me I h bar dn dot e to the minus I en0 t over h bar plus I h bar dnt. I have to differentiate the second function, which is minus I en0 over h bar times this whole thing times n0. Okay, this is the first piece. So what is this equal to? This is equal to IH bar dn dot. So what is this? The h bar cancels here. I times minus I is plus, right? Yeah, plus en0 e to the minus. Okay, this is the first piece. Is this clear? This is the ddt part acting on the right hand side. The second part is minus h0. So, okay, so let me actually underline this equation. So I'll just add all the underlined equations. The second part is minus h0 acting on dn of t e to the minus I en0 t over h bar n0. And you know that h0 acting on n0 is just en0 n0, the eigenvalue equation. So this is equal to minus dnt en0 e to the minus I en0 t divided by h bar n0. That is my second piece. Okay. And my third piece is minus h tilde dnt and since I don't know how h tilde acts on these guys, I will just have to keep it as it is. There is no further simplification I can do. Okay, so the right hand side of this equation is the addition of the three underlined greens, and you immediately see that this term cancels this term. Okay, if that term cancels that term, whatever is left out gives you the simple differential equation. What is that? IH bar dn dot of t e to the minus I en0 t over h bar acting on n0. That is the first term here. Minus h tilde dnt e to the minus n0 equals 0. Okay. Now I can take off the e to the I en0 t completely. And now see the magic appear. So I have gotten rid of h0 completely. And in this equation, I can divide through by the e to the minus I en0 t over h bar. And I can get rid of the en0 also completely. So this turns out to be a differential equation that is solely dependent on the d's and the h tildes. So I can rewrite this differential equation as IH bar dn dot of t minus d of t h tilde of t acting on n0 equals 0. Is this clear? Okay. Now, sorry, I forgot the sum over n, right? So I'll just do the sum over n. So I started with sum over n of this. So I'll have to introduce a sum over n. Because I've written the general state psi as a linear superposition of the unperturbed states n0 with a time dependent coefficient. Is this clear? Yes or no? Any questions about this? It looks like we are making progress, but this is still a little difficult to do. Why? Because in this equation, I remember that I do not know d, and I also don't know what is the action of h tilde on n. Okay. So this makes it slightly more complicated. So I need to write this in terms of something simpler that I can calculate. Of course, this is something I can simply plug in and solve this differential equation. But it turns out that I can actually massage this into a slightly more manageable form. The way I will do this is I'll multiply this equation. Now I will not get rid of the e to the minus IEN0t over h bar. Okay, I'll just retain it because there is nothing wrong with retaining it. So I'll write the minus IEN0t over h bar n0. Okay, and then I'll multiply this equation by the bra m0 times e to the em0t over h bar. Okay, now you can easily guess where I'm going with this. The first term, the dn is just a number, right? So it's just a function, it's not an operator. So the m0 can go right through the dn and the exponential to hit the n0. So this splits into two different terms. The first term is IH bar dn dot t. Okay. There is an e to the plus IEM0 and minus IEN0. So I can write this as e to the I EM0 minus EN0 t over h bar M0 N0, that is the first term, minus sum over n d of t, again e to the I EM0 minus EN0 t over h bar times. Now remember that the n0 cannot be taken to the right because there is a operator h tilde sandwiched between. So this is the h tilde sandwiched between the unperturbed eigenstates. So if you have revised your time independent perturbation theory, you should see the structure emerging. It's the same thing as what happened in the correction to the energy eigenvalues of the time independent perturbation theory case. Remember that the correction to the first order correction to the energy eigenvalues is basically the expectation value of the perturbation part of the Hamiltonian between unperturbed states. I'm not saying this is exactly the same, but a similar sort of structure emerges. This is M0 H tilde of t n0. This is equal to 0. Okay. Now the first part is easy. This is just delta mn. So the first part is not a sum anymore. It is just one particular term with m equal to n. So I'll write that down. IH bar dm dot of t e to the I omega mn t equals sum over n d of t e to the I omega mn t times m0 h tilde n0, where I have defined my frequency omega mn as em0 minus en0 divided by h bar. E is h bar omega, so E over h bar has the units of frequency. Okay. So this is the setup of the problem. I have now transformed the Schrodinger equation into a differential equation for D. So now I will in principle tell you how to solve this as a perturbation, because it is still not obvious. I think I missed a. So this is a D.
Sir?
Right. This is a D. Excuse me. Just 1 minute. I'll
Yes.
correct this typo. Yes, please go ahead.
Sir, in the left hand side, you have e to the power I omega mnt, but when you use this Dirac delta function, when you use the delta function, won't your n naught and m naught become equal? So that
Yes, you're
exponential term will
absolutely right.
vanish.
Yeah, you're right. You're right. Thank you. Yes, yes.
Yes.
Very good. So I will not have this on the left. Very good. IH bar dm dot of t equals this. Yeah, that is a differential equation. Thank you.
Yes. Okay.
Any other questions or comments? See, so you might think that this is easy to solve. After all, I know m0s and n0, so this part is a calculable thing. This matrix element is calculable, right? Because I am given h tilde, so I can always calculate this matrix element. There's no problem. But the problem with this differential equation is that any solution to dm also depends on d. See, the d appears both on the left hand side and the right hand side. Right? If the right hand side does not depend on d at all, this is a trivial equation to solve, right? This is just a first order differential equation. But that is not true, because the right hand side also is a linear combination of the d's. So I will, tomorrow I will set up this as a perturbation theory by claiming that I can write this d as a perturbation in h tilde in some small parameter, which I will simply call h tilde. Now the right hand side is already first order because there is a manifestly there's an h tilde, right? So I will solve it order by order, and I will tell you exactly how to treat this as a perturbation and solve for d order by order in perturbation theory. Okay. So I will stop at this point here because I have set up the differential equation for d for the time dependent problem, and we will discuss how to solve this tomorrow. Okay, and then we'll also discuss some terminology like what is a sudden perturbation and things like that. Okay. So today I will just stop at this point, and we will